We will explore how to create a schedule, which is a model for executing a project's activities. This model includes details like durations, dependencies, and other planning information. Schedule planning can use either predictive or adaptive approaches. When using a predictive approach, we follow several key steps. First, we decompose the project scope into specific activities. Second, we sequence these activities. Third, we estimate the duration required for each activity. The primary tool for sequencing activities is the Precedence Diagramming Method, or PDM. This method helps build a project schedule network diagram. It defines 4 types of logical relationship between activities. The first and most common type is finish to start. Here, a successor activity can only begin after its predecessor activity has finished. For example, installing an operating system can only start after the computer hardware is fully assembled. The second type is finish to finish. In this relationship, a successor activity can only finish after its predecessor activity finishes. Think of furniture placement waiting for paint on a wall to dry before being completed. The third type is start to start. This means a successor activity can only start once its predecessor activity has started. Using the same painting example, painting the walls can only begin once moving the furniture out has started. The fourth and least common type is start to finish. Here, a successor activity can only finish after its predecessor activity starts. An example is a new payment system only being able to finish its launch after the old payment system begins its phase-out process. The output of this sequencing step is the project schedule network diagram. After sequencing, we estimate activity durations using various techniques. These include expert judgment, analogous estimating, 3-point estimating, and bottom-up estimating. Once we have durations, we develop the schedule using schedule network analysis. This is an iterative process to create a viable schedule model. A key technique within this is the critical path method, or CPM. The critical path is the longest sequence of dependent activities in a project, determining the shortest possible project duration. For this analysis, we typically assume all relationships are finished to start. It is crucial to note that activities on the critical path have a total float of 0, meaning they cannot be delayed without delaying the entire project. Let's clarify the difference between total float and free float. Total float is the total amount of time a task can be delayed without delaying the project finish date. Free float is the amount of time a task can be delayed without delaying the early start of any immediately following task. We calculate total float as late start minus early start. We calculate free float as the early start of the next activity, minus the early finish of the current activity, minus 1. For instance, in a sample diagram, if the critical path is activities A, B, E, and F taking 15 days, then activities C and D are not on the critical path. They might have total floats of 2 and 1 day, respectively. Next, we have resource optimization techniques. Resource leveling adjusts the schedule so that a resource is not overallocated, often by having them work on only one task at a time in a given period. This can change the critical path. Resource smoothing adjusts activities only within their available float without exceeding predefined resource limits, but it may not optimize all resources perfectly. We also use data analysis. What if scenario analysis asks questions like, what if a specific situation occurs, to evaluate the schedule under different conditions? Simulation, like Monte Carlo analysis, uses a computer model to run many iterations, creating a probability distribution of possible schedule outcomes. We also manage leads and lags. A lead is an acceleration, where a successor activity can start before its predecessor finishes. A lag is a delay, where a successor activity must wait after its predecessor is complete. Finally, if a project is behind schedule, we can use schedule compression. The 2 main techniques are crashing and fast tracking. Crashing adds more resources, like extra people or overtime, to shorten the duration, but it increases cost. Fast tracking changes activities originally planned in sequence to instead happen in parallel, often by applying leads or lags in the schedule network. For example, in a diagram, activity 4 might start 1 day before activity 2 finishes. This is a lead. In another case, the normal finish-to-start relationship is broken, and activity 8 must finish 1 day after activity 7 finishes. This waiting period is a lag.